So just like we learned how to graph every single exponential function, we have to know what every single log function looks like. So here we're going to graph a basic log graph, log base 4 of x. And this base, this is a basic parent graph of a log 1. You should be able to graph anything with any base there. So the fact that this one's a 4, after doing this one as a 4, you should be able to do a 3, a common log, log base 7, any base you'll be able to graph. So how do we know what a log graph looks like? Well, at the beginning you might have to think of your exponential functions. And you might have to think that if the base is 4, a log graph is an inverse of an exponential graph with the same base. So off to the side you might say, well, I know that the graph of 4 to the x has 0, 1 and 1, 4 and an asymptote at y equals 0. So at the very beginning when you start graphing logs, you might think of your exponential graph to help you. Later on, you're just going to be able to graph them just like you know what an x cubed graph looks like now, you know what a square root graph looks like now. You're going to say, I just know what a log graph, because all log graphs look the same. They all have 1, 0. Does that make sense? If you think about all of your exponential graphs, all having 0, 1, does it make sense that all of your log graphs are going to have 1, 0? And since the base is 4, I'm going to have the point 4, 1. If you did a log base 7 graph, you'd have 7, 1. A common log, you'd have 10, 1. All log graphs have this shape. And all log graphs will have an asymptote at x equals 0. So identify the intercepts. Well, there's no y-intercept, but there is an x-intercept at 1. All log graphs, because you're always going to have 1, 0, right? So they're going to have the same x-intercept. I mean, it's going to change once we do transformations, because if you move this up and to the right, things are going to change. But your parent graphs will always have an x-intercept at 1. The equation of the asymptote will always be at x equals 0 for any parent graph of a log graph. The domain of a log graph will be x bigger than 0. And the range of a log graph will be everything. In fact, if you think about the exponential that we drew at the top, what's domain and range? Here, the domain is everything, and y was bigger than 0. And all that's happened is x and y have switched. Later on, we're going to do all the transformations of log graphs, but right now we're just starting with parent graphs. So you now can draw any parent graph. We're going to do one more example. I think you have space at the bottom of 378. Yes? So we're going to do one more example at the bottom of 378. And that is we're going to graph the natural log of x. So there's a common log and a natural log. The common log has a base of 10. Any guesses what the natural log has a base of? It's not of 1. No. No, not 100, not 17. It's a number that you probably wouldn't have talked about a lot before this unit. It has a base of e. So this is the same as log base e of x. And it's called the natural log. And it's ln, I think, from French. Logarithm naturel or something fancy like that. Probably. Okay? So, I think there's a lot of French influence in math. So natural log ln. What letter do we use for slope? M. It comes from the French word for mountain. Anyways, not the English word for mountain, even though that starts with M too. So we have y equals natural log of x. All log graphs go through what point? 1, 0. And this one's going to go through e comma 1. All log graphs have an asymptote at x equals 0. And they follow this shape. Nice. So, practicing graphing some basic logs. Question 10 and 11.